right, good afternoon, everyone. Welcome to our first Applied Physics Colloquium of the quarter. It's my distinct pleasure to introduce our speaker today. I should say that our speaker, Professor Feng Wang from UC Berkeley, is also here as the Hanna visiting professor, and that means that he's actually around Stanford for some period of time, and I'm sure he would be very happy to talk to any of you who'd like to follow up later. Feng received his undergraduate training at Fudan University in China. He got his PhD at Columbia University and subsequently was a Miller Fellow at UC Berkeley. And they seem to have liked him so much they didn't let him go, and he continued on the physics faculty where he's now a professor of physics and a senior faculty scientist at the Berkeley Laboratory. Feng has made wonderful contribution to understanding reduced dimensional systems, typically but not exclusively using optics, and these include contribution to understanding carbon nanotubes, graphene, two-dimensional semiconductors, and particularly in the recent period of time, combinations of two-dimensional semiconductors. So he's really done some marvelous work, and just to give you an idea about his range of activities and his productivity, he actually gave a condensed matter physics seminar a couple of weeks ago that some of you may have attended, and it was a very nice seminar, and I said, happened to be an opening coming up soon because of a cancellation here, and I said, Feng, could you give this talk? I said, well, I have to give a completely different talk. That'll take me a couple of weeks. So here we have the completely different talk a couple of weeks later, which you'll see is on electron-hole fluids and van der Waals heterostructures. Let's welcome Feng.
Oh, first I would like to thank Tony for the invitation, the host, and he forgot to tell you that I also got PhD from Tony, so I learned all the optical spectroscopy from the master. And it will be it's a great pleasure to spend time at Stanford more frequently and meeting many of you, and I hope that I have more chance to interact with more of you. So today I will tell you some of our effort, kind of more like baby steps, trying to explore this electron and hole fluid in two-dimensional semiconductor heterostructures. So if you think about low energy physics in general, chemistry or biology, almost everything is governed by Coulomb interactions and quantum mechanics. So if you have attractive and kind of a repulsive Coulomb interaction between positive and negative charges, you can form atoms. The atom can take and leave, give charge to form ions, and furthermore, they can the atom can combine to form atoms or the solid, and even kind of large biological molecules. So if we think about solid state physics, we tend to focus on the quantum phase of electrons. So in that case, the Coulomb interaction is still there, but it's mostly repulsive kind of electron-electron Coulomb interaction. When you have the repulsive Coulomb interaction with quantum mechanics, we found that many interesting things can emerge from it, from Mott insulator magnetism and superconductivity to Wigner crystals to integer and fractional quantum holes. So extremely rich behavior. But you can't help to wonder, well, what if we also add attractive Coulomb interactions? Would that open up even more opportunities or let us to explore more exotic phases? So if you go beyond kind of a ground state physics in solid state, we find we actually are pretty familiar with a situation where you have both attractive and repulsive interactions. And that is when you shine light onto a solid. In that case, you excite the electron, so you have negative charged electron, and you also leave positive charged holes. And these negative and positively charged particles can attract each other. So if you have two of them, they can form like hydrogen-like bond state known as excitons. Or if you have some residue electron around, then the electrons and the excitons can together form trions. Or if you have multiple excitons, they can even form four-particle bond state like biexitons. And if you excite many of the electron hole together, they can form electron hole plasma. So this multiparticle or complex in principle can host a lot of interesting physics beyond simple like repulsive electrons. However, in most of the optical excited state, there is a limitation, that is most of these multiparticle state are transient state and they have relatively short lifetime. So it's kind of difficult to study or the kind of a quantum phase diagram of these many multiparticle composite. So the question is, can we actually realize this attractive and repulsive interaction in a system that can kind of exist close to ground state, so they can live for a long time, so we can probe them more systematically. And the idea is actually pretty old. In the study of gallium arsenide quantum well, people basically imagined if you have electron hole in two different layers, then you can basically have attractive interaction between electron holes and the repulsive interaction between the electrons. And this basically is known as a coupled 2D electron hole bilayers. So in order to explore their phase diagram, the most important parameter to some extent is the separation between these two adjacent layers. You want this separation to be large enough so that the electron hole do not recombine, so they can live for a very long time. But at the same time, you want the separation to be small enough so that the electron hole attractive interaction remains very strong, so you can form different type of bound state. So since the discovery of graphene, turns out the best system to realize this electron hole bilayer is this atomically seen heterostructures. Because people realize that you can actually exfoliate many layered material in these atomically thin sheets, which can be semiconductors, which can host the electron holes, and they are insulators that can form very good barriers. And furthermore, we can simply stack this individual layer together to form this heterostructure to design or basically anything that you want. And one example is this transition metal dichalcogenide. So these are 6 examples. They have different size of band gap and different band alignment. So if we just choose 2 of them, say MOSE2 and WSE2, they have so-called type 2 band alignment. The conduction band minimum is in MOSE2 and valence band is in WSE2. So if you simply stack them together, the conduction and valence band don't overlap. So you don't naturally have electron hole bilayers. But what we can do is we can stack them with a thin BN in between. With this exfoliation technology, we can actually control the BN down to a single atomic thick, which is 0.4 nanometer, or we can choose each integer number of layers. So we'll focus on a range where the thickness is from, say, 0.4 nanometer to around 3 nanometer. And furthermore, we can put electrical contact to individual layers. So with this electrical contact, we can apply bias or gate voltage so that we can inject electrons and holes into these 2 bilayers. Or it was estimated the exciton binding energy with this kind of HBN thickness can be in the 10 to 100 milli-electron watt range. Or 100 milli-electron watt if you convert it into temperature, that is about 1000 Kelvin. So, okay, so with this electron hole bilayer, theorist was always ahead. They predict many interesting phases that can emerge. So if we create a situation where the electron hole charge density are exactly balanced, then the electron hole basically can form tightly bound excitons. So an exciton is a boson. So we know that with this boson, if you go to very high temperature, you basically have this boson gas. So they can last to 100 Kelvin. You have this tightly bound exciton gas. And then if you lower the temperature, then the de Broglie wavelength of the thermal exciton becomes longer and longer. Sooner or later, it can be larger than the separation of the excitons. So we basically can reach degenerate boson gas. And if you lower the temperature further, one should be able to reach exciton condensate that can live at tens of Kelvin or maybe even higher. So compared with atoms, because the exciton mass is much, much smaller, and the exciton density we can realize is much, much higher, so you don't need to go to or nanokelvin to get the Bose-Einstein condensate. You can get it at tens of Kelvin. So at least that's the hope. So beyond the excitons, we can also inject the electron-hole with different density. For example, if they have a 1:2 ratio, it was predicted they can form these so-called interlayer trions, where you have one electron in one layer, but bound to two holes in the other layer. And these trions will be a charged particle, fermion. So at very low density, just like electrons will kind of crystallize as electron Wigner crystal, these trions are also predicted to form a trion Wigner crystal. And then if you vary the density of the trions, if you go to intermediate density, quantum fluctuation of these trions will melt it into a trion fluid. But if you go to even higher density, then this electron-hole basically can screen the interactions and you go to an electron-hole Fermi liquid. So it will be quite interesting to see how the different phases actually evolve when you vary this just trion density. Of course, you don't have to fix the electron-hole density to be just 1:1 or 1:2. You can continuously vary the density ratio. So in principle, one can have a mixture of excitons and trions and free carriers and so on and so forth. It's also possible to form even higher order composite particles. So in principle, there are a lot of opportunities to explore, and they so far have been little studied. So that's kind of our main motivation, trying to kind of or start to look into this electron-hole bilayer system. So today I will tell you basically, these are my outlines. So first I will tell you how we realize it experimentally, these electron-hole bilayers, and I will tell you how we will mostly use optical spectroscopy to actually probe what's going on in these electron layers and hole layers in terms of charge density and the spin. And then using this kind of optical technique, I will show you that we can probe this interlayer exciton phase diagram, not only in ground state, but also how the exciton actually can transport as a function of basically in real space and in real time. And lastly, I will tell you how we can observe this three-particle state where you have the interlayer trion fluid. So, okay, so I will start with the first topic. So here is basically illustration on how we kind of make these electron-hole bilayers. So we start with MOSE2 and WSE2 two semiconductor layers. We put a thin BN in between. So initially we'll use a relatively thick BN so that it actually allows us to kind of create the electron-hole bilayer more easily with more manageable applied electric field and bias voltage. So we have several different kind of voltage applied to every single layers. So with 4 voltage, we can control basically 3 voltage differences. And that allows us to vary in different parameters. So let's start with this kind of a pristine heterostructure. We have WSE2 and MOSE2. So Fermi energy lies in the gap. So both layers basically will be undoped. So first, what we can do is vary the bias voltage between MOSE2 and WSE2 layer. So when you add a bias voltage, what you do is you shift the electrochemical potential or Fermi energy of these two layers relative to each other. So what you can see is if you shift the Fermi energy or large enough, say larger than the initial band gap, excuse me, then we'll dope electron into one layer and hole in the other layer. So you will inject this electron-hole fluid. Equivalently, we actually can use a vertical electrical field to or reach the final goal. And the idea is if you apply a vertical electrical field, because the two layers are at a different z position, so the potential energy basically will be shifted differently. So as a result, the vertical electric field will be able to shift down the conduction band relative to basically the valence band. So if the field is large enough, then we can shift down the conduction band to be even below the valence band. Then in that case, even at zero bias voltage, you can basically have a hole doped in this layer and the electron doped in that layer. So these two knobs effectively do the same thing. They kind of change the chemical potential and band alignment. As a result, they will allow us to inject equal number of electron and hole doping in the system. So in reality, we all tend to use both of the knobs, because if you use only one of them, very often you exceed the breakdown electric field of HBN. So you kind of need to use both effects together, so that allow us to finally reach the electron and hole doping. So also, the other knob we can have is basically the symmetric gate voltage. So if we have all the same positive voltage at the top and bottom gate, what we can see is it will attract electrons. So it can change the create a net electron doping. And if you use negative gate voltage, you can create a net positive doping. So basically, these gate voltage allow us to basically tune the ratio of the electron and hole density. So with these two together, we can basically control the electron density and the hole density separately. So if we add the electron and hole in the system, one question is like, oh, how do we characterize them? So one thing with this interlayer electron hole bilayer is they live for a very long time. That means they don't emit and they usually don't absorb light effectively. So we can't really use, say, photoluminescence of this interlayer exciton to probe them. So what we do instead is we will probe the behavior of the electron and the hole separately through optical spectroscopy. In order to do that, I will explain to you what people actually know quite well in terms of a doped monolayer TMD. How does the optical spectrum change? So this basically shows the optical reflection, which you can think as an optical absorption spectrum, as a function of the gate voltage, and then vertical axis is basically the wavelength. So on this side, the gate voltage basically cannot dope carrier in the system. So in this region, the WSE2 is basically charge neutral. If you do a vertical cut, you can see there's a very strong resonance here. And this resonance corresponds to creation of bound excitons. And then when you go along this direction, the hole will start to dope in the system. So this basically corresponds to increased hole doping. And when you have increased hole doping, what you can see is that this exciton resonance gets shifted and also gets reduced. But at the same time, you see a new resonance comes out. And this is a kind of a intralayer trions, where the exciton excited in WSE2 is bound into with a hole to lower its energy. And the energy is lowered by about 30 millieV, so that's the energy difference between these two states. So the trion binding energy for this intralayer system is about 30 milli-electron-volt. People have also done a lot of calculation and characterization to visualize this exciton and the trion behavior. So this intralayer exciton trion has a characteristic size about 1 nanometer. So they're actually very tightly bound behavior. Because the optical spectrum change very strongly with the hole doping, we can basically map the optical spectrum to the hole doping 1-to-1. And the idea is, so for this system, basically we only have gated two-dimensional hole gas, which is very well understood. So as a result, we can basically map the gate voltage into hole density using a capacitive model. So once we do that, then we can convert this gate voltage versus spectrum into hole doping versus spectrum. So in this case, so what you can see is the spectrum has 1-to-1 correspondence to the number of the hole density in the system. And the same procedure can be done for the MOSE2 layer. So this is basically the optical spectrum as a function of electron density. So again, what you can see is if there is no electron density, there is a very strong resonance corresponds to excitons. When you have increased electron density, the exciton resonance gets reduced and shifted, and then there's an emergence of the trion resonance.
Can I ask a question?
Yes.
This is reflectivity in absolute units. You've got R at 0.5. You have a single layer of electrons doing this? Making that much reflectivity?
Yes, so it turns out actually with the okay, so I need to double check this, but I can tell you with a single layer sitting on a kind of a substrate, because the exciton oscillator strength is really, really strong, and it's also very sharp. It can indeed create a reflection change of 50%. So maybe this is more like delta R over R. But I would like to tell you actually, or people have shown, if you put it on a metal, a monolayer actually can absorb all the light. Just because the oscillator strength is really very, very large for this monolayer TMDS. Okay, so with that in mind, so we have, or at least if you have only hole-doped layer or electron-doped layer, we have a one-to-one correspondence to, from optical spectrum to carrier density. So the idea is now if we have bilayers where we have both electrons and holes doped at the same time, or can we use the same mapping to actually determine electron and hole density by looking at the spectrum? So here I just show the experimental spectrum when you apply a large enough vertical electric field and large enough bias. So in the middle region, that actually corresponds to electron and hole are simultaneously doped. So for example, if you look at the top resonance come from the MOSE2 layer, you can see the exciton feature, but also the trion feature. That means there are electrons in the MOSE2 layer. So the bottom part actually corresponds to the optical transition in the WSE2 layer. Again, you see the exciton feature and the trion feature. That means the hole is also doped in this system. So you can see electron and hole are indeed simultaneously doped. If we do a line cut, we can basically plot the optical spectrum. So that is the black curve. On top of that, we can superpose the absorption spectrum of the WSE2 layer when it is only hole doped, and the MOSE2 layer when it is only electron doped, and that is this kind of a colored plot. So it turns out we can match this co-doped region almost perfectly to a specific spectrum when it is only electron doped or only hole doped. So with that, basically, we can actually determine the electron density and hole density separately. So you might be wondering, why does it work so well? So I mean, when you have an electron hole possibly bound into exciton, why doesn't it affect the kind of, or the intra-layer exciton resonance and the trion resonance? So the answer to that, somewhat hand-wavingly, is we can actually make an analogous to core level spectroscopy with X-rays. Because this interlayer exciton and the trions are really tightly bound, so they are probing behavior like with kind of nanometer scale or relatively high energy. So as a result, they're actually not so sensitive to whether there is another hole in the adjacent layer. Similar to the X-ray core level transition for atoms, they are very element specific. When it is bound to other kind of atoms in a molecule, it only lead to a very small change. So because of this effect, we can actually use this calibrated spectrum and carrier density method to basically determine at every position what's the local electron density, what's the local hole density using optical spectroscopy. In addition to measure the charge density, it turns out the optical spectroscopy in transition metal dicogenite also provide a powerful way to measure the spin density. And the idea is, like this, Tony and many others have shown previously, the transition metal dicogenite, the band minimum, sit at two different momentum in the Brillouin zone, known as K and K prime value. And these two values have very different optical selection rules. So if you use left circular polarized light, you can only excite excitation in K prime value. And when you use right-hand circular polarized light, you can excite excitation only at the K value. At the same time, this system has very strong spin-orbital interaction, and that leads to a phenomenon known as spin value locking. So what it means is if you add a hole into K prime value, it's always spin down. And if you add a spin up hole in the system, it will have to go to the K value. So with this information about optical selection rules and spin value locking, we can actually ask now, not what happens to the exciton transition, but what happens to the trion transition. So imagine we add a spin down hole in the system. Then because of the spin value locking, we know the spin down hole has to sit at this K prime value. Oh, sorry. Okay, so spin down hole is at the K prime value. So in this case, if you use a circular polarization like sigma plus that measure exciton in the same value. So what you can see is this excited exciton and the residue hole, or they will have the same spin for these two holes due to Pauli kind of or blocking phenomena. When you have two holes with the same spin, they cannot form a bound trion state. So in this case, you will not see any trion resonance. On the other hand, if you add a spin up hole in the system, then it has to go to K prime value. Again, if you use circular polarized light to excite exciton in the K value, then in this case, these excitons and that hole, because these two holes now have opposite spin, they are very happy to actually form a bound trion state. So as a result, by using circular polarization and look at the trion resonance, you can actually tell whether the hole is sitting at K or K prime value, or equivalently, you know whether the hole has spin up and spin down. And experimentally, this can be demonstrated by looking at the trion signal as a function of magnetic field. For example, if you apply a positive magnetic field, say you will kind of align all the spin up, then all the spin will be at the K value. And if you use sigma plus polarization, you can see a very strong trion signal, and it becomes stronger when you have larger magnetic field. But if you have opposite magnetic field, you see the behavior is completely opposite. With the negative magnetic field will push all the spin to be spin down, and then it will go to the K prime value. Then in this case, it cannot form bound trion anymore. So the trion resonance basically have zero oscillator strength. So then use circular polarization to measure the trion behavior, then you can actually tell the intralayer trion signal. You can tell what the whole spin is. So with that in mind, we can then use this kind of method to characterize the electron-hole, correlated electron-hole behavior in this electron-hole bilayers. So first, again, this just to remind you the heterostructure we have. So we will have the MOSE2 and WSE2 layers separated by about 3 nanometers. We will fix the vertical electric field to be a relatively large value by setting the top and bottom gate voltage difference to be 11 watt. So that just helps to reduce the effective band gap of the conduction and valence band. On top of that, we will apply a bias voltage. If it's large enough, it will induce electron-hole co-doping. And we can also control the kind of symmetric gate voltage that control the net charge density. And these two map basically shows the electron density and the hole density as a function of the bias voltage and then the gate voltage. So basically what we can understand is, or if you do a horizontal line cut here, basically we see that at relatively small bias voltage, then the conduction band and the valence band do not overlap. So in that case, you can create only electron doping or hole doping, but not at the same time. So what you can see is with this gate voltage, you can create electron doped layers. And in this range, you will create hole doped layers, but there will be a middle part that you have no electron or hole doping. But when the bias voltage is large enough, what you can see is then you can create basically electron doping over here and hole doping over here. So basically you can create electron hole doping at the same time. So with this kind of a density mapping, then we can take a closer look and see how the electron hole density change correlatedly based on the different control knobs. So here I just reproduce the kind of electron and hole density map. So if we measure the exciton compressibility, which is defined as, or if we modulate the bias voltage a little bit, how would the exciton density change? So if you have kind of or exciton that can flow in the system easily, then you will have finite exciton compressibility. So the exciton density is basically defined as the or smaller one of the electron density and hole density. So if you basically have equal number of electron and hole density, you have that number of excitons. But if you have some excess charge, so only the smaller number of charge basically will be able to form the exciton density. So what you can see is in this kind of a region, you can have finite exciton compressibility. Basically, you can inject excitons in the system. But at the same time, we can also measure the charge compressibility. That is, when we apply a gate voltage, how much can we inject net charge in the system? So what we can see is if you have only electron-doped region and only hole-doped region, you can basically inject either electron and hole in the system. In the region where you don't have electron and hole, of course, you cannot inject any carriers, so that's the insulator gap. But the interesting part is basically within this top region where the exciton has finite compressibility. So over this part, the charge compressibility is also finite. But there is a very small triangle region where although we have net electron and hole density and we can inject excitons into the system, but we cannot inject individual electron or individual hole to the system. And this region is known as exciton insulator. Basically, that means you can inject excitons, but not the individual carriers, and it can be reproduced in many different samples. Yes?
I have a question. In this little slice here, I see a lot of pink dots in there. Is
Yeah.
it really a slice? And what happens if you take the black arrow out?
Okay, that's a very good question. So that's why we also initially are not how sure that the signal-to-noise ratio is not very good. So these are basically the reproduced signal in kind of 3 different samples. So when the sample quality changes a little bit, sometimes the compressibility doesn't really go to 0. But I think in some other samples you can see they are definitely strongly suppressed compared with outside. And so similar behavior was actually first reported in electrical transport method by the Cornell group. And then the explanation is basically, at this bias voltage, the conduction band and the valence band are getting very, very close to each other, but still not overlapping. So in that case, you cannot inject electron and hole in the system, but it's possible to inject a combined exciton in the system because excitons have lower energy compared with individual electrons and holes. So we can actually look at this region more carefully, say by calculating what's the chemical potential for electrons and holes. So the idea is we have all these gate voltage and bias voltage, and the bias voltage really control the electrochemical potential. But then if we also know the electron hole density, we can actually solve the Maxwell equation to determine what's the electrical potential. So with the electrochemical potential controlled by the bias voltage and also the electrical kind of static potential, we can use this information to calculate what's the chemical potential of the electrons and holes as a function of electron hole density. And this is basically kind of the chemical potential for electrons, chemical potential for holes as a function of electron density and hole density. And this is a chemical potential for the mu E plus mu hole, which is the exciton chemical potential. So in this mapping, what you can see is at the diagonal direction, there's a very clear feature in this chemical potential for electrons and chemical potential for holes, but not so much for the excitons. So we can understand this feature a little bit better by just doing a line cut. So here I just kind of, again, reproduce the chemical potential and look at the chemical potential change as a function of the electron density when the hole density is fixed at about like 0.2 10 to the 12 per centimeter squared. So what you can see is the chemical potential of the electrons have a general kind of dependence on electron density due to the electron-electron interactions. But then there is a jump of chemical potential when the electron and the hole density equals to each other. And this jump is about 10 or 13 milli-electron volts. And when you look at the chemical potential of the holes, it has the same magnitude but the opposite sign, a chemical potential jump. So this chemical potential jump, we think, is related to the exciton binding energy. And to understand it, what happens is when the electron density is less than hole density, so we have excitons and also a lot of free holes. When you inject an electron into the system, they can always form a bound exciton. So it has low energy. But once you have the electron density larger than hole density, when you inject the electron in the system, it cannot form exciton anymore. It can only form a free electron. So as a result, there is an energy difference between these that's associated with, corresponds to exciton binding energy. And we can use this as basically a way to determine the exciton binding energy and see how does the exciton binding energy change as a function of the exciton density. So what we found is that exciton binding energy actually decreases monotonically with exciton density, and it goes to almost 0 at a density about 0.8 times 10 to the 12 per centimeter squared. So this is what our theory call a Mott transition between the exciton fluid into an electron hole, degenerate electron hole plasma. Okay, so these are basically the quasi-static behavior of this exciton phase diagram. So next I would like to talk about how we can actually probe or somewhat dynamic behavior, how this exciton transport, and then look at correlated electron and hole transport. So when you have electron and hole bilayers, one way to look at them is to direct the electrical transport measurement. For example, if you have contact to the layer at the same time, you'll find it's not possible to pass a current through it, because if it's only bound excitons, it simply cannot, it's a neutral particle, it cannot carry net charge. On the other hand, if you can make separate contact to the electron and hole layer, what you can have is you can pass a current in the, let's say a drive current in the hole layer, then the exciton means the electron and hole will move in the same direction. So there will be an electron current, electron basically charge density moving in the same direction. But because electrons carry opposite charge, it corresponds to the electrical current that move in opposite direction, but have the same magnitude as this drive current. Another way people can do is actually make this so-called counterflow measurement. So in this case, again, you have pass opposite current in the two layers, which corresponds to the basically excitons moving in the same direction. So if you have a superfluid, then it will be a dissipative current flow. If you measure the potential drop, let's say in this whole layer, then you'll find there will be 0 voltage drop. This electrical measurement, although looks very simple in this cartoon, is actually very difficult to do experimentally because it's very hard to make good electrical contact to this electron and hole bilayer at the same time. So what we'll do is trying to find some kind of alternative ways to measure this optical transport. And then what we do is actually use optical detection to kind of determine the effective transport property. So the idea is like that. So we'll still use a device that's similar to what I have shown before. So the only change is now we will actually split the global backgate into 2 parts. So basically we have 2 partial backgate. So initially we'll apply a DC voltage to basically create homogeneous exciton population in this system. And then what we'll do afterwards is we will use AC modulation of this partial gate voltage. So what will happen if you modulate this gate? So let's assume if the electrons and holes are not forming excitons, so you have free moving charges, then if you apply, say, negative gate voltage, it will attract the electrons, it will attract holes, or it will push electrons away. On the other hand, if you have bound excitons, so if you apply a gate voltage, what you can think happening is basically you will change effective field, electric field over here. So as a result, you modulate the energy of the exciton, so it will be able to actually drive a exciton current flow. So with this gate voltage, what we will do is we will use optical readout to measure the local electron density as a function of position and as a function of time or frequency. So in this case, basically, we can see how electron density is changing and how hole density is changing. That basically tells us electron current and hole current. And we can see whether they are correlated and how they correlate with each other. Okay, so here basically we just measure with 10 kilohertz modulation of the gate and measure the induced change of electron density and hole density, which will be correlated to induced electrical current and hole current. So as you can see here, we use a kind of a modulated backgate, which is close to the hole layer. So if the electron and hole are not coupled too strongly, so we can think we are mostly gated the hole layer, so that we can call this or the hole current as the drive current. And then the electron one, you can think it as like a drag current type of thing. So first, let's consider the hole current. What we can see is as long as the system is hole doped, you actually have very strong, basically, gate-induced hole current. But then when we look at, so this part basically shows the electron current, and we actually see very different behavior. So if you look at the low bias voltage, in that case, or you have hole doping here, but then in this region you have only electron doping. So in that case, when you basically modulate the gate voltage, you find that the electron density change actually have opposite sign compared with the hole density change, because they have opposite charge. If you apply positive gate voltage, you will repel holes but attract electrons. So the electron density change and hole density change have opposite sign. But things become completely different when you have both electron density and hole density. Then in that case, the hole density change and the electron density change actually have the same sign. So that means you actually have a pretty strong drag signal in all these phase diagram. And this drag signal is particularly strong within this triangle region. So if we actually do a ratio between kind of this hole current and then the electron current, we can actually find the drag coefficient is almost 1, kind of over here. So we can do some line cut and to look at it more carefully. So for example, if we just do a horizontal line cut, that means we will change the kind of electron hole balance. So the green curve shows the hole current, and then the red curve shows the electron current. So the ratio of them basically reaches almost 1 within experimental uncertainty, like at electron hole density 1-to-1 ratio. And then if you start to add excess electron holes, this drag signal remains significant, but it becomes smaller. Similarly, we can go along this charge neutral line. So that means we have only exciton in the system, but we have more and more exciton density. We find that the low density of excitons, the drag is close to 1, but at higher density, the drag actually becomes smaller. So maybe because a lot of excitons start to get dissociated. So those measurements happens at a single frequency. So what we can also see is when we modulate the system at different frequency, how would the electron hole response actually change? So here basically we measure, basically show the electron current and hole current in the kind of exciton region. So what you can see is their response are identical at all frequencies. So that means the electron holes are really dynamically moving together. And both of them basically show a characteristic kind of a decreased frequency at about 1 megahertz. So we can think about this decreased signal at higher frequency using an effective circuit model. So, or in the case we have only excitons, we can simplify this the model to be basically there is an effective resistance for exciton flow, and then at the two gate we have effective capacitance for this exciton, and the RC constant basically will determine this transition frequency. So also, well, what is the capacitance and the resistance for exciton? So we can kind of make an analogy to charge behavior. So the capacitance can be defined by Q over V. So basically we can have derivative of exciton density versus the kind of voltage on exciton, which is defined as the difference between the hole layer and the electron layer voltage. And then the resistance basically is V over I. So we can define it as, again, the ratio between the voltage, exciton voltage, divided by the exciton current. So the capacitance can be simply calculated in the system when we know the geometry of the system. And then basically, by measuring this characteristic frequency, or we can determine the effective resistance of this exciton. So here basically shows the kind of exciton resistance we measure as a function of exciton density. So you can see the exciton resistance, effective resistance is still pretty large. It goes from megohm to the high tens of kilo ohm. And it decreases with exciton density roughly following a 1 over density behavior, which is kind of a classical behavior that one would expect. We can also measure it at a different temperature. So this is a resistance as a function of density and as a function of temperature. So what we see is it doesn't have very strong temperature dependence. If you look carefully at high density, the exciton resistance actually decreases a little bit. So this measurement initially is very disappointing for us. We are really looking for exciton condensate, where you should have very small exciton resistance, but we haven't observed it so far. So based on theory and based on the exciton density and the temperature, if we have an ideal system, it should already be in degenerate boson gas regime. So there should be some interesting kind of Bose-Einstein condensation behavior. But the fact that we don't see it experimentally maybe is because our system is still kind of too much disorder, it's not clean enough, and it's basically we are trying to make better samples to push this further. Okay, so last I will tell you beyond the excitons, we can also look at kind of or multiparticle kind of bound states such as or interlayer trions, and maybe possibly beyond. So in principle, if we have both attractive and repulsive interaction, as I mentioned, one can form trions, biexcitons, and so on and so forth. However, this multiparticle state becomes more and more sensitive to the layer-layer separation. Because if you think about the exciton, they are always attractive. So if the layer distance become larger, you just decrease the attractive potential by 1 over r. So it has strong distance dependence, but it's more manageable. If you look at the trion, the behavior is actually different. So if you increase the layer separation, the attractive interaction between positive and negative charge decrease. But then the repulsive interaction between these two adjacent electrons doesn't change as much. So as a result, the kind of a trion is much more sensitive to the layer-layer separation. And indeed, theoretical prediction shows that the trion binding energy decreases very quickly. And also above kind of a critical separation, the trion simply cannot exist anymore. So with that in mind, if we want to study trion, we know what we need to do is actually make the distance as small as possible. So we kind of modify our system a little bit. We now go to MOS2 and WSU2 heterostructure, just because the band kind of offset between these two is a little bit more favorable. So overall, they have slightly smaller band gap. Then we can use a thin PN and use large electric field to basically close that gap to create electron-hole bilayer. So in this case, we will make the HBN to be only 2 or 3 layers. So it's like around 1 nanometer. So here I just show you the kind of optical spectrum when we inject the electrons and holes in the system. On the left-hand side, we apply a relatively small bias voltage. In that case, we can have only electron doping in this region and hole doping in this region. So what you can see is when it is electron doped, we can see the exciton and the trion feature for the MOS2 layer. And when it is hole doped, we can see exciton and trion signal for the WSE2 layer. So on the right-hand side, I show the behavior when you apply large bias voltage. So now you can inject the electron and hole at the same time. So again, at 1:1 ratio, you can see the exciton and the trion, exciton and trion. So basically, both regions are doped. But if you look carefully, there are also some kind of additional spectral change that happens around this region that happens to be the density of electron hole is 1 to 2. And if we zoom it out, we can see this spectral feature is actually pretty obvious. So you can see this original trion, intralayer trion signal disappears, and a new feature appears. So if we zoom in the kind of corresponding region for the electron layer, or if you kind of squint your eyes, you might say there might be something happening at 2/1 where the spectrum becomes a little bit broader, but it's very hard to see. And the reason is initially this peak is very broad. So it kind of make the small change kind of harder to detect. So as a result, we'll just focus on the whole doped region where the whole density is twice of the electron density and look at this spectral feature more carefully. So first, I just reproduce the spectral feature. So what you can see is this kind of the intralayer trion peak, which we call X plus peak, kind of disappear here, but then a new peak appear. So this corresponds to one line cut in this bias voltage and gate voltage kind of a phase diagram. So we can also focus on only at one wavelength, say just add this X plus wavelengths, and then look at its behavior in this two-dimensional phase diagram. So what we can see is this intralayer trion signal is present almost everywhere when you have hole doping in the system, except along this 1 to 2 line. So it really tells us this spectral feature is associated with kind of a specific doping ratio between electron and holes. So something is happening at that multiplex. But in order to kind of establish conclusively this is a kind of a bound trion state, it's actually better to look at the spin correlations. So first of all, let's just remind us what happens if you have only free holes in the system. So if you have free hole, it have kind of a spin that can be polarized with magnetic field. I have shown you previously if you kind of apply magnetic field, you can polarize the spin, and then use circular polarized light. You can see this is fully polarized in one spin, and this is fully polarized in opposite spin. Now we can look at the magnetic field dependence for this new kind of spectral feature. So also just let's focus on the top dashed line first. So what you can see is this feature actually is largely symmetric to the positive field and negative field. That means the magnetic field is actually not polarized in this state. So it's an indication that the hole in this system is actually more like a spin singlet configuration, so which will be kind of corresponds to a bound trion. Because if you have a bound trion, the electron is bound with two positive charge, and to lower its energy, the two hole has to have opposite spins. So since they have net zero spin, when you apply a magnetic field, you cannot polarize them. So the behavior is symmetric. But you might ask, oh, what happens at large magnetic field? Why does it disappear? And then we start to see this trion signal very strongly. And that can be understood basically by thinking about the energy difference between the bound trion state versus this exciton and free carrier state. And how do they change when you apply magnetic field? So the trion binding energy, or relative to the free hole and the exciton, is not that large. So when you apply a magnetic field, because the trion hole spin is singlet, the energy doesn't change. But then one component of this exciton plus free hole energy actually keep decreasing with larger magnetic field. So what you can have then is with large enough magnetic field, most of the trion will start to get dissociated or basically get into this state. So as a result, you start to see this free hole kind of density start to increase. And then at high density, high magnetic field, the trion signal decrease. And we can kind of do a line cut of this and basically fit this behavior quantitatively. And by using this simple model, we basically can extract the trion binding energy, which is about 1 milli-electron volt. So it's about 10 times smaller than the exciton binding energy. So with this understanding, we kind of now know that basically the P plus peak really tells us the trion density. And then the X plus peak basically tells us, what's the free hole density. So now if we look at this spectrum and when we change electron density, we can actually read out, what's the trion density and what's the free hole density and how do they evolve, let's say, when we change the electron density. For a fixed hole density. So basically what we can see is initially when we have 0 electrons, so everything, all the holes are free, so you have very large kind of trion signal, but no, this interlayer trion signal, but no P plus signal. That means you have no trion. And when you add electrons, so the electron basically will kind of grab 2 holes and form trion, and it will reach a maximum when the electron hole density is 1 to 2. And when you keep increasing electron density, then the electron will actually take additional holes from the trion and form exciton-trion mixture. So in this case, the trion density will start to decrease. And if you keep increasing electron density, in principle, you will form exciton and the electron trion, and then electron and the trion mixtures, which cannot be read when we only probe holes in the system. So with that, basically, we can actually have this electrically controlled boson and fermion or fermion-fermion mixtures where you have different electron and the trion mixtures and exciton-trion mixtures. Okay, with that, I come to my conclusion. So I hope I have shown you when you have this atomically thin semiconductors, it's actually a very nice platform to have both electron holes so that you can have competition between attractive Coulomb interaction and the repulsive Coulomb interactions. So we can see that the interlayer excitons is actually tightly bound and is a very well-defined composite. It shows perfect Coulomb drag because the electron and the hole needs to move together even for exciton gas without a kind of exciton condensate. And then I also show that you can form this kind of a 3-particle trion state, and you can have mixture of exciton and trion states. So I think these are all basically early works. I think they really bring up many open questions. So one big question is, when can we see high temperature exciton superfluid? I think in principle it should be there. All we need to do is make the sample better. But if we can indeed have this high temperature exciton superfluid, there are very interesting possibilities to explore the exciton circuit, such as, say, this Josephson junction made of exciton superfluid. So for trions, in principle, they can form Wigner crystals. So can we image them directly and see how the trion Wigner crystal melting will be different from electron Wigner crystal melting? And furthermore, like if you have, say, or if we can create exciton in superfluid case, and now when you add charges to form trions, or how do you even picturize this kind of exciton superfluid then with kind of charged trions? And there have been some theoretical proposals saying that they can even lead to novel superconductivity behavior. So many things to explore in the future. And the last, I'd like to thank people who made this work possible. So Ruishi Qi is a really talented graduate student that spearheaded most of this work. In the initial study, he works closely with postdoc Andy Zhou, who is now in UC Riverside. He also get help from other students in the group. For theory, we have a nice help from Alan McDonald, as well as Liang Fu from MIT. The transition metal dicogenized sample from Arizona State, and the BN sample from Japanese group. And thank you for your attention.
questions? Yes.
Hi. Maybe I have a couple of questions. One is the excitonic superfluid. So is there, the way I understood it is these are kind of, it's an equilibrium system because it's a ground state, but is there a fundamental difference if this superfluid was formed of interlayer excitons, which have some, let's say, which are of course which have a finite lifetime but can emit light. Is there a difference in the, say, many-body physics as long as the thermalization time scale is short enough compared to the lifetime?
Yeah, so especially when you have excitons and when you have relatively thick BN, like say 2 or 3 nanometers thick BN, we know the lifetime, the lower bound is close to like a second. So in all the microscopic kind of time scale, I think that's almost infinite. So I think the thermalization for them should not be a problem. So compared with say atomic BCs, the thing is like it is actually it is a dipole exciton, so it has a very large dipole moment. So these excitons will be rather strongly interacting. So it will be kind of quite interesting to see how this strong interaction actually is reflected in superfluid state if we can observe it sometime.
So I guess my question was, is there a difference between these excitons and if you had an excitonic superfluid formed by tungsten diselenide, molybdenum diselenide in contact, so.
Oh, okay. Yeah. So
you actually see, you can see that.
That's right. So yeah, so the main difference is now with HBN, the lifetime is much longer, although the exciton binding energy is reduced. If you don't have HBN in between, then the lifetime of the electron and holes are actually only at, say, tens of nanosecond. So there's a serious question whether they will be able to thermalize effectively. And also, in this case, you can actually electrically gate and inject the electron holes. So when you have 2 layers directly on top of each other, I think electrical injection also becomes much harder. Usually people use optical excitation, and that actually create more kind of excess heat in the system. So it will make the system more complicated.
Just another short question on when you had the magnetic field data. Isn't it that? So I was thinking, when you apply a magnetic field, the electrons in the K valley are spin up, and the holes in the K prime are spin down, right? So then if they are layer separated, isn't that also spin up electrons in the top layer, spin down holes in the bottom?
Yeah, so what happens is like, in this probe, it doesn't care what the electron is. So because we are only probing the whole layer, so what you can see is kind of this type of thing. So the spin of the holes will affect the spectrum strongly, because you are creating excitons in the kind of WSE2 layer. So it will be very sensitive to the spin configuration of the holes present in this layer. I mean, electrons doesn't contribute to all these optical transitions, so it doesn't really play any role. So if you want to ask whether the electron spin actually affected the formation of the interlayer trion itself, it also doesn't matter, because the electron is in a different layer, so there is no negligible exchange interaction. So basically the electron spin that, yeah.
Another question, yes please.
Just estimate maybe. What is the interlayer exciton lifetime in these systems?
Interlayer exciton lifetime. Okay, so it depends on the HBN thickness very strongly. For the part that we mostly study the excitons, we use 2 to 3 nanometer like thick HBN. The lifetime, based on the leak current, we estimate the lower bound of the lifetime is hundreds of milliseconds. So it's kind of 100 millisecond to second. Though if we push the HBN to be really thin, only kind of say 2 layers, then the lifetime is more like 100 of nanosecond, microsecond. So it depends on the HBN thickness very sensitively.
Yes.
I'm interested in the practicalities of this. I mean, I didn't get to see any of these samples, but you did mention that it's difficult to connect the two layers together, yet you are able to make contact to them independently. Why is that? I would think if you can make contact to them independently, you could connect them electrically.
Okay, yeah, that's a very good question. Sorry, I didn't explain it. We do make electrical contact, and but in electrical transport measurement, they actually the electrical contact have two roles. One is it can serve as a contact to gate the sample. So in that case, even a very bad contact works fine, because the leak current is very, very small. So even if you have a contact with megaohm or tens of megaohm, you can still use it to gate the sample. And that's what we are using it here. So you can still gate it to inject electrons and inject holes. But if you want to use those contacts to measure electrical transport, say resistance and mobility and so on and so forth, you want the contact resistance to be at kiloohm range. And that is very hard. So that means we can make a bad contact that's sufficient for gating, but we cannot make a good enough contact to do nice electrical measurement.
Yeah. I'm curious about the drag experiment in the regime of trion fluid, I guess. Can you expect to have fermion fluid dragging your bosonic fluid with it? Imagine flowing a current in the electron-rich layer. Would that drag your spheric insulator alone, or what's the picture there?
Yes, yes. So that's a very good question. So in principle, yeah, there should be some unusual drag behavior. So far, like all the type of sample that we made, all this split gate and that we can measure the transport, are happening with a slightly thick HBN. So in that case, we think the trion might still be present, but the trion binding energy is so small at our measurement temperature, then there are a lot of free electron holes at the same time. So we don't see the trion signature very clearly. So we plan to do it in a dilution fridge. When we go to lower temperature, then those trion may be still very well defined. And in that case, we should be able to see some interesting drag behavior when you have trions or mixture of exciton and trions. So
maybe just a quick follow-up. Incidentally, do you have any independent probe for measuring the yield of formation of bond state versus free charges, or is the drag the best indication possible there?
Also, the ratio between the trion and then the free carrier density actually can be read out. Okay, so when the HBN is very thin, it can be read out basically by reading the intensity of this peak versus that peak quite well. Yeah, again, when we go to thick HBN, it becomes a little bit tricky. So we kind of have to infer it without this direct spectroscopy signature.
You sort of indicated that all of these things are in their smallest spin state. Do you ever get them in excited spin, like a spin 3/2 trion or a spin 1?
Yeah, so if you have spin 3/2, basically they cannot form a bound state anymore, because if you have okay, at least in this regime. Liangfu actually has some calculation. If the electron and the hole mass are very, very different. So in that case, it's actually possible to form a trion even when the two very heavy holes have the same spin. So when the electron and hole mass are comparable, I think the theory calculation shows like if the two holes have the same spin, basically the lowest energy state is not a bound state. But then if they have opposite spin, you can have a bound state. Yeah, I think it's just the energetics of this multiple particle versus like whether that allow you to form a bound state or not. But yeah, but like I said, in some regions, so you actually could have all the spin along the same direction. So if one layer mass is much heavier than the electron layer, then you can actually have high spin trions. And that will still have high energy compared with a low spin trion, but what you can do is you can apply a magnetic field to polarize it. So then you can have a net high spin trion.
So Feng, you mentioned two very nice concepts. One was sort of a Wigner crystal in the context of the trions,
The other was an exciton condensate. And so there, the simple picture is more or less non-interacting bosons. The other one's strongly interacting fermions. But isn't the reality somewhere in between? Because as you mentioned, actually the interaction between the excitons is pretty substantial, and maybe one order of magnitude at most lower than the interactions between the charges. So, I mean, you said the repulsion would be very interesting for the condensate, but is it favorable or unfavorable? It seems like it's sort of, at odds with creating a condensate.
Yeah, that's a very good question, actually. I tried to ask a theorist, but I do not get a consistent answer. I mean, some... Yeah, okay, so I can say what I heard from read some paper basically says the interaction is actually favorable to form superfluid. Because actually if you don't have interaction, the superfluid is actually not stable. So they claim the interaction is favorable. But I have the same question as you. If the interaction is so strong and repulsive, maybe it will prevent it to condensate. Yeah, so I actually don't know. Yeah.
So the theory, I'm a theorist.
Yes.
At zero temperature with no dirt, there is a competition between superfluid order on the one hand and crystalline order on the other.
I see.
So the insulating state in those conditions would have positional order, and it would be a crystal of these excitons. All of these problems, it's a competition. So when you say excitonic insulator, my brain hears crystal.
Okay.
Because I can't think of any way to write down an insulator state at zero temperature that makes any sense. The superfluid of excitons makes total sense, and the crystal of excitons makes total sense. But anything else, I don't know what that is. Just words.
That may be the right place to stop. Carry on for the refreshments. Let's thank Feng Wang very much.